Every next-generation aircraft program currently in development, the Boom Supersonic Overture, the Airbus ZEROe hydrogen aircraft, the NASA X-59 quiet supersonic demonstrator, the various hypersonic platforms under development in the United States, China, and Russia, every single one of them must eventually operate in the same environment, an environment that commercial aviation has largely avoided for 60 years of jet travel, the stratosphere. Above 40,000 feet, above the weather, above the clouds, above the troposphere where virtually all commercial aviation operates. The physical environment changes in ways that the engineering assumptions underlying current aircraft design were never built to handle. The radiation levels increase by factors that matter for both passengers and materials. The atmospheric chemistry responds to engine exhaust in ways that do not occur at lower altitudes, and that have consequences for the ozone layer that aviation regulators have only recently begun to quantify seriously. The temperature, pressure, and density relationships that aircraft designers work with below 40,000 feet begin to behave differently in ways that affect every aerodynamic and propulsive calculation in the design. And there is a deadline. Not a political deadline, not a regulatory deadline, a physical one. The race to solve the stratospheric problem in next-generation aviation is one of the most consequential and least reported engineering challenges of the next decade. Let me show you exactly what the wall looks like, and why the industry is more concerned about it than anyone is publicly saying.
The stratosphere begins at approximately 36,000 feet at mid-latitudes and extends to approximately 160,000 feet. Commercial aviation operates primarily between 28,000 and 40,000 feet in the upper troposphere and the very lowest stratosphere. The Concorde operated at 55,000 to 60,000 feet, firmly in the stratosphere. Boom Supersonic's Overture is designed to cruise at 60,000 feet. The NASA X-59 will operate at similar altitudes. Hypersonic platforms under development operate at 80,000 feet and above. At these altitudes, the atmosphere looks the same to the eye. The physics are profoundly different. The first difference is radiation. At sea level, the Earth's atmosphere and magnetic field shield living tissue from the majority of galactic cosmic radiation, high-energy particles originating from outside the solar system, and from solar particle events, bursts of high-energy particles emitted during solar flares and coronal mass ejections. At 36,000 feet, normal commercial cruise altitude, the radiation dose rate is approximately 100 times higher than at sea level. The FAA classifies flight crew as radiation workers specifically because of this exposure. At 60,000 feet, the stratospheric cruise altitude of next-generation supersonic aircraft, the dose rate is approximately 4 to 5 times higher than at 36,000 feet. For a passenger on a 3-hour transatlantic supersonic flight at 60,000 feet, the radiation exposure is comparable to a chest X-ray. For every flight. This is not a classified finding, it is a published measurement. What is not publicly discussed is what this means for the regulatory certification of supersonic passenger operations, and what it means for crew members who fly these routes daily, for years.
The radiation problem is the one that affects passengers. The ozone problem is the one that affects the planet, and ultimately, every aviation program that depends on regulatory approval to operate. The ozone layer sits primarily between 50,000 and 130,000 feet altitude, directly in the operating range of supersonic and hypersonic aircraft. The chemistry is precise and well established. Water vapor injected into the stratosphere participates in catalytic reactions that destroy ozone molecules. Nitrogen oxides, NOx, produced in engine combustion at high temperatures, catalyze a separate and more efficient ozone destruction pathway. At lower altitudes, where commercial aviation operates, these effects are negligible. The atmosphere is dense enough that the exhaust disperses rapidly, and the chemistry is different. In the stratosphere, where the air is 1,000 times less dense than at sea level, exhaust products persist longer. The chemical pathways are different. The catalytic cycles run longer. The Concorde program generated this concern in the 1970s, and studies at the time suggested the Concorde fleet was too small to produce a measurable ozone effect. That conclusion was correct for a fleet of 14 aircraft. It is not correct for a fleet of 1,000. Boom Supersonic projects a market for 1,000 Overture aircraft over 10 years of production. United Airlines alone has options on 50 aircraft. If 1,000 supersonic aircraft operate stratospheric routes daily, the ozone chemistry becomes a regulatory problem of the first order. NASA's High-Speed Strategic Transport Environmental Research Program has been modeling this specifically. Their preliminary findings have not been publicly released in their complete form, but the regulatory implications are already being discussed in closed IKA working groups 2 years before the first supersonic passenger flight.
The ozone concern applies to conventional hydrocarbon-fueled supersonic engines. Hydrogen propulsion, the technology Airbus is developing for its ZEROe aircraft program, targeting entry into service in 2035, eliminates carbon dioxide and most particulate emissions. But hydrogen combustion produces one thing in larger quantities than any conventional fuel: water vapor. Hydrogen burns to produce water. That is the entire point. Clean combustion, no carbon. At ground level and low altitude, water vapor from hydrogen combustion disperses rapidly and has no meaningful atmospheric effect. At stratospheric altitudes, where the ZEROe long-range variant would need to operate to achieve the range and efficiency targets that make it commercially viable, water vapor injection into the stratosphere drives exactly the ozone chemistry described in the previous section. The cleaner the fuel, the greater the stratospheric water injection. Hydrogen aviation, if it operates at stratospheric altitudes, could produce ozone effects comparable to or exceeding those of hydrocarbon supersonic aviation, not despite being clean, but because of it. This is not a theoretical concern being raised to block hydrogen aviation. It is a documented chemical reality that the ZEROe program's engineering team is actively working to address by evaluating whether long-range hydrogen operations can be conducted at altitudes that avoid the most sensitive stratospheric layers, and what that altitude constraint does to the range, efficiency, and commercial viability of hydrogen-powered long-haul aviation. The answer to that question will determine whether hydrogen can replace kerosene on intercontinental routes or whether it is confined to short and medium-haul operations where the altitude constraint does not apply.
There is one final dimension to the stratospheric problem, the one that ties radiation, ozone chemistry, and hydrogen propulsion together into a single systemic challenge. It is called the solar cycle. The Sun operates on an approximately 11-year cycle of magnetic activity, moving from solar minimum, when galactic cosmic radiation reaching the Earth is highest, to solar maximum, when solar particle event risk is highest. The next solar maximum is projected for 2025. The stratospheric radiation environment during solar maximum is significantly more variable and potentially more intense than during solar minimum. A major solar particle event, a sudden burst of high-energy particles from the Sun, can increase stratospheric radiation at 60,000 feet to levels requiring immediate descent to lower altitudes. Current commercial aviation already monitors solar activity and occasionally reroutes polar flights during major events to reduce crew and passenger exposure. For supersonic aviation at 60,000 feet, where descent to safer altitudes takes longer and costs more fuel, the solar event protocol represents a genuine operational constraint that does not have an equivalent in current aviation. Boom Supersonic's Overture is designed with descent capability specifically to address this scenario. But the regulatory framework for managing solar particle event risk at supersonic cruise altitudes does not yet formally exist. ICAO's aviation system block upgrades for high-altitude operations are still in development. The FAA has not yet published its radiation exposure standards specifically for supersonic operations, and the ozone monitoring framework that would detect and regulate the cumulative atmospheric impact of a commercial supersonic fleet is not yet operational. The aircraft are being built. The physics problems they must solve have been identified. The regulatory infrastructure to manage them is running 5 years behind. The invisible wall does not care about commercial timelines. It was there before aviation existed. It will be there when every aircraft currently on the drawing board is already retired. The engineers designing the next generation of aircraft know what it is. The question, the one that determines whether supersonic returns, whether hydrogen flies long haul, whether the next 60 years of aviation look as different from today as today looks from 1963, is whether they can solve it before the aircraft they are already building need to fly through it. Follow for more about the physics at the frontier of commercial aviation, the problems that are real, the timelines that are funded, and the barriers that the industry does not always want to discuss publicly.